All right, welcome back again, everybody, and welcome to Chapter 16. We're finally entering the world of vector calculus, so things are going to get super exciting. They're really, really cool. Calculus 3, a lot of the stuff that we talk about throughout the beginning of the course is really just to build you up for what we're going to learn in this chapter and these sections. So let me pull up the slides and we'll get started. All right. Okay, so the first section of this chapter is really just about vector fields. So we're kind of setting the stage for the objects that we're going to be working with for the rest of the chapter. Here's the overview. We'll just do a quick introduction about, just motivation for the chapter kind of thing. Then we will talk about vector fields, define them, see some examples. We will cover a couple basic applications, some that you might have actually heard about before. Oh, fix that. There we go. Um, then, yeah, some basic applications. Then we'll talk about gradient fields and then conservative vector fields, which are going to pop up throughout the chapter. And then I'll end with some helpful Mathematica commands, but really I'm going to pepper these throughout the section, throughout the lecture. So I won't dwell on it too much at the end there. I'll just kind of show you these examples in Mathematica so you could see them and see how to do them yourself at home. All right, so here we go. This chapter is where we're basically going to put together about like everything you've learned in all your previous calculus courses. It showcases the beautiful connections between math and physics, and it prepares you to study in a rigorous way the complex ideas that permeate our reality. So one of the things that I like to say before the class starts, before like literally in my intro email to my Calc 3 class, I always encourage people to go outside and feel the wind on their skin and in their hair, and just kind of imagine if you could see the wind and how it would be contacting your body and how it flows around you, right? Because now we're going to start to talk about the mathematics related to to those feelings, you could say. We're also going to prove several important theorems for your edification, and then also to examine the methodology of the proofs themselves, because you may encounter such methods later. So math majors in particular, one of the things that you want to study is proof techniques. So not so much like what the proof is, but how did you actually prove that thing? Because you'll see that pop up over and over again. And then the other thing I'll add is just that the chapter builds upon fundamental concepts learned in this section. So just make sure you're comfortable with what a vector field is and that kind of thing, and you should be good to go. Oh, hold on one second. Let me adjust my camera. All right, there we go. That's a little bit better. Okay, so here's the definition to get started. What is a vector field? So let's start with a subset D of n-dimensional space. Then a vector field is a function that goes from that region you chose in n-dimensional space and maps to V sub n. That's the space of n-dimensional vectors. And what this vector field does is it assigns to each point in that set an n-dimensional vector f of x. So a vector field is essentially a vector valued function. And what you're doing is you're taking a point in space and you are assigning a vector to that point. That's the basic idea. So in R2, so for example, in the plane, what a vector field does is it takes a point xy in the plane and it maps it to a two-dimensional vector given by f of x comma y. So you could think of it, remember what is a vector, right? It's basically something that gives you a direction and a magnitude. That's what this is doing here. It's saying, hey, at that point, let's associate this direction and magnitude. And we're going to see lots of cool applications in a minute here. Same thing in R3. If you're in three-dimensional space, a vector field takes a point x, y, z and maps it to a three-dimensional vector given by f of x, y, z. That's the basic idea. Here are some figures from the book. So here's a vector field in R2. And again, the basic idea is pick a point in space, maybe the point x comma y, and at that point, associate a two-dimensional vector, which is indicated by this arrow right here. So at the point x comma y, this function f of x comma y is this vector that you see right here. So it's kind of like saying if you were at that point, go in this direction this far. And you're going to do that for every single point on the plane, not just the ones that are depicted here. I mean, here there's a few shown just for example, but it would be literally every point on the plane, every single point you would associate a vector based on the point. Same idea in 3 dimensions. So here's kind of what a 3D vector field looks like. And we're going to look at a couple in Mathematica as well, so you can get some more intuition. But the idea is the same. Pick any pick any point in three-dimensional space and associate with that point a vector at that point. Basically, where would you go at that point and how far? Some more realistic applications or maybe less abstract applications are, for example, wind patterns. So if you've ever looked at a wind map like this, maybe if you're just looking up the weather for your own, where you live, this is what it is. So these little arrows here that you see all around correspond to a vector, right? They're vectors that are saying which way the wind is going and how fast. That's a vector field. So what we're doing is we're taking a point or any point in the plane, and we are associating a vector to that point. So here's another example of it here at a different time. So this vector field changes depending on the time, naturally, right? Ocean currents. So for example, ocean currents are modeled by vector fields. You basically figure out which way the water is going at a point and how fast, and then you can describe it as a vector field, just like so. You can even do this in 3 dimensions, right? You can talk about the fluid flow in a 3-dimensional sense. It doesn't have to just be like a 2-dimensional projection, right? Here's another one. So anybody that's interested in aerodynamics and stuff, you're going to be studying a lot of vector fields. Here's a vector field that shows how the air flows past, is this right? Oh, sorry, this way, flows past an airfoil or, essentially a wing, right? And you want to explore and you want to model how the air flows over and under and around that wing. You do it with vector fields. And this is why we care about vector calculus. So just to reiterate a little bit and draw a connection to what are called scalar fields, think about it like this. So because f is a vector function, what you can do is you can write it in terms of its component functions, right? So vectors, you have all these components. We can talk about the component functions, and what we can do is explore those component functions individually. So let's say f is an n-dimensional vector, and we're going to let x be this position vector. Then we can denote the component functions of capital F as f1, f2, dot, 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 all the way up to fn. And we can write the vector field, capital F, as a vector that is evaluated at all of these component functions. So first component function f1 evaluated at x, f2 evaluated at x, dot, 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 fn evaluated at x. And that's what f is really doing, capital F. Now, the component functions themselves, they're often called scalar fields because they're scalar valued. So for example, they're real valued. So f1 of x is going to give you a real number as an example, right? It'll be a real number for that component direction. And then the same is true for all of these. So a lot of times we will call these functions scalar fields just to distinguish them from vector fields, so that it's clearer what we're talking about and what the objects are at play. Just to add here, this is one of the reasons why way back in chapter 12, I had those questions where we explicitly asked, is this thing a vector? Is this thing a scalar? Does it make sense to dot these two things? Does it make sense to cross these two things? This is one of the reasons for that, just to set you up for this kind of a confluence of ideas at the end of the course here. All right. So in the 2-dimensional case, we can describe our vector field F in terms of its component scalar fields. We can call the first one P, and we can call the second one Q. And these are individual scalar valued functions that are dependent on x and y. So this is saying, hey, give me a point x, y in the plane, and this is how the vector behavior is going to be in the I direction, and this is how the vector behavior is going to be in the j direction. And it can be independent, right? The way that these things change, they don't have to be linked up. They're just describing how you would be moving in those component directions. And here, P and Q are scalar fields. They're scalar valued functions. So you put in a point x, y, and you get out a real number. That's the idea. Same thing is true for 3 dimensions. Same thing is true for 4 dimensions, and just any number of dimensions. In 3 dimensions, you'll have 3 scalar fields for your component functions, just like so. P, Q, and R. You give me a point in 3 space. This says how the vector is going to behave in the I direction. This says how the vector is going to behave in the j direction. And this says how the vector is going to behave in the k direction. And that's how a vector field can be written in terms of its component scalar fields. Okay, now let's look at an example. let f of x comma y be this vector field here, negative y times I and x times j, and just sketch f, right? So this one is one I do actually want you to try on your own. So first, just think about it and think about what it's asking for a moment. All right. Now, like usual, say something out loud. Doesn't have to be to anybody in particular, but just make sure that you are saying something out loud to give your brain that feedback. Maybe what you would draw first, or what's happening in the I direction versus the J direction. Just say something out loud. Okay, now try to make a quick sketch. So maybe start by drawing, some coordinate axes, pick a point on the plane, and then see what vector you get at that point, and then try to sketch that vector. And we'll do it together in a moment and look at it on Mathematica. Okay. All right, here we go. So if you pick some sample points and then you and then you evaluate f at these sample points and then you sketch the vectors, you get something that looks roughly like this. Remember that this is actually true for any point in the plane. So this is only a small sample size of what the vector field would actually look like, quote unquote. Some attributes that you can pick out. First, notice that as x and y grow larger in size, the length of the vector also grows as well. So in other words, the magnitude of the vector. It's not really too difficult to see if you look at it algebraically as well. So like if I pick the point here, this is the length of the vector. But then if I go farther away, the length of the vector is going to be longer because one of these two components is getting larger. So the length is going to grow. So as you move away from the origin, these vectors are going to grow in magnitude. And as you shrink down to the origin, the vectors are going to shrink in magnitude. That's the idea. It also at least appears like these vectors are tangent to some circle that's centered at the origin. Even, this one seems like it's tangent. These ones are all tangent to a circle. So we'd like to verify that, right? This is just kind of our intuition. It appears this way, so how could we verify it to make sense of it? We're going to take the dot product, right? How do you determine orthogonality? Well, I should say if this is going to be tangent to a circle, then it's going to be orthogonal to its position vector, right? So what we're going to do is we're going to take the dot product of the position vector of any one of these points, and we're going to dot it with the vector given by f of x comma y. And that's what we're going to do. All right, here we go. So here's v, and we dot it with f of v. So remember, v is just the position vector of any given point x comma y. So, pay close attention that it's not this vector field here. V is this. It's just the position vector of the point x comma y. And if we dot it with f of x comma y, we get this. And then when you do the arithmetic, you get negative xy plus yx, which equals 0. So our intuition that all of these vectors are indeed tangent to a circle centered at the origin is correct. That's what's happening here with this particular vector field. Also, notice that what do I have here? Length of v is that, length of that is that. Oh yeah, so notice also that the magnitude of the vector that you get at a point is actually equal to the radius of the circle that it lies on. So that's what this is saying here. The length of v is x squared plus y squared, and then take the square root. And the length of f of x comma y is going to end up being the same thing. It's going to be the length of v again. So not only are these vectors tangent to these concentric circles, but the length of the vector or the magnitude of the vector is actually equal to the radius of the circle. So the length of this right here is equal to the radius of the circle here that goes like that. So this is one behavior being described by this particular vector field. Okay, now how about this one? So, oh wait, you know what, before I go to that, let's take a look at what this looks like on Mathematica. Let me show you that first. Let me go back to this, and let me pull this up, Mathematica. All right, here's what it looks like in Mathematica. Yep, you can see that. I put some basic options just to make the graphs look a little bit pretty, but the Mathematica command that you want to use for a two-dimensional vector field is vector plot, just vector plot. And remember that Mathematica takes a list denoted by curly braces as a vector. So in our case, this is the vector negative y, x. That's the vector that's the vector f, capital F. We're just going to choose x to be between negative 3 and 3, y between negative 3 and 3, and then this is the plot that it produces. Now, what is this? How do we interpret this? So this plot is a little bit different from the figure that we just saw, because in the figure, the magnitude of the vector was being shown by the length of the arrows. In this plot, the magnitude of the vector is being indicated by the color. So the color legend is right over here. So the bluer the arrow, the smaller the magnitude of the associated vector at that point. So one thing I want to point out, notice it is a circular vector field, right? So those arrows that we were seeing before, wait, other way. Arrows that we were seeing before are the same. But now as we go from inside, or sorry, as we go from the origin outward, the color of the arrows are changing to indicate that the length of those vectors is getting longer, or the magnitude. So very, very close to the origin, your vector's magnitude is almost zero. Far away from the origin, your vector's magnitude is getting large, and it'll grow increasingly large as you move away. All right. Okay, now let's go to look at the next example. Let's look at a vector field in R3. So this is one that you don't have to worry about sketching it. I feel like it's much easier to understand what it looks like using Mathematica or using some other computational device. But here is the vector field. Here's the rule for it. ZK. So for every point in three-dimensional space, the vector that you're going to associate with that point is just zk. So x and y don't appear here. So x and y are not going to affect the vector field. The only thing that's going to affect the vector field is the z coordinate of the point. And what it's going to do is it's going to take that z coordinate and scale the k direction vector by that amount, right? So here's what it looks like. This is a figure from the book, but we'll look at it in Mathematica in just a moment. So like I said, it doesn't depend on x or y. It'll scale the vector k by whatever the value z is. So what it's going to look like is a bunch of vertical rays. And the further away you get from the xy plane, the longer the rays are going to get, right? So just think about as z gets larger, the magnitude of this vector is going to get larger. And as z gets closer to zero, the magnitude of that vector is going to get closer to zero. It's going to shrink down, right? So let's take a look at Mathematica again. Here we go. And that one is right here. Okay. So let me explain a little bit of this here. So if you want to plot a three-dimensional vector field in Mathematica, the command is vector plot 3D. And because we need to actually give it a three-dimensional vector, I filled out the zero component functions right here. So the coefficient of the I direction would be zero, coefficient of J would be zero, coefficient of K is Z, like we saw. That's the actual vector field. Just choose some somewhat arbitrary bounds for X, Y, and Z, negative 3 to 3, and so on. And then this is what it looks like. So this is one of the nice things about Mathematica, is you can move this stuff around and really examine what the vector field looks like. Hard to do on when you're only looking at a sketch, right? So let me do this first. So for one, the spacing of the arrows is really just an artifact of the sampling. In order to produce this picture, Mathematica has to sample the space, essentially. Pick some points in the space and then evaluate this vector function at that point to produce the arrow. So it's just doing a random regular, I shouldn't say random, it's doing a regular sampling. But again, the magnitude of the vector is being given by this color gradient right here. So the more bluish the vector is, the shorter the length of the vector is, or the smaller the magnitude. So remember that as z gets close to zero, that means the magnitude of the vector is going to get close to zero, and that's why these vectors here are more purpley, because they're getting close to zero. The value of z at, what is this, maybe, oops, maybe like, looks not quite a half, maybe like 2/3 or something like that. It's under one, but something like that. And then it's going to evaluate the vector field at all those points and produce those arrows. Now, as z gets larger, let's say in the positive direction, then the magnitude of the vectors gets larger. So that's why these arrows are becoming orangish and then yellowish. And then as you keep moving away, they would get longer in magnitude. Same thing if you were to go in the negative z direction, because in the negative z direction, it's the same thing, right? It's the same thing. It's just the sign is different. So now you're pointing down instead of pointing up. All right. Let's get back to the slides here. Excuse me. So as far as applications go, there are uncountably many applications of vector fields. I don't even know if it's possible to, yeah, it's not possible to describe every possible application. It's just not possible. But they're an incredibly ubiquitous and powerful object. They're really good for modeling things that you really want to explore in reality or even in your imagination. So that's why we study them. Here's a very simple example. Perhaps this is an example that you have thought yourself. I'm sure you have felt it before if you've played around with water and hoses, maybe in like the shower or the bath or like when you're washing your hands. Here's an example, right? So imagine fluid flowing steadily through a pipe, and we're going to let v of xyz be the velocity vector at any point xyz in space. So then what v is doing is it's assigning a three-dimensional vector to each point in some region in space. So this is literally a vector field by definition. Because these vectors are modeling velocities, this vector field is often called a velocity field. That's what's happening here. So you can see here that the velocity is quicker here in the tube when it's a little bit shrunk, when it's squished down. But then as the tube opens up, the velocity decreases. There's more room for the water to flow. So the velocity is decreasing, it's slowing down. Okay. Here's another one. So this is a popular one. Newton's law of gravitation states the magnitude of the gravitational force between two objects with these two masses is given by this formula here. So physics majors, I'm sure you've already heard about this a while ago and you've thought about it deeply. Now you get to think about it even more deeply. Here, r is the distance between the two objects and g is the gravitational constant. So we're going to look at this vector field in just a moment here. We're going to get a formula for the vector field and then look at it in Mathematica as well. But yeah, remember gravity is essentially pulling on things, tugging on things, trying to get them to come inward toward it, right? So let's do this. Let's suppose the object of mass m2 is located at the origin in R3. So for now, we're going to consider this a three-dimensional space. We're going to let the position vector of the object with mass 1 be x, the vector x, x, y, z. So position one mass at the origin and position the other mass elsewhere, all right? And what we're going to do is we're going to let the coordinates of that point where mass 1 is located be the components of this vector, x, y, z. Now, because r is the distance between the two objects, this makes things easy because r is just going to be the length of that vector x. And so r squared is equal to x squared. There you go. Now we're going to convert this formula. So the gravitational force that's exerted is going to be acting toward the origin because this thing at the origin is pulling stuff into it. And we want to know how much force is exerting on that other mass, right? So a unit vector in the direction of the origin is given by negative x over length x, right? So it's a unit vector. We have this formula here to give us the length, and now we have a unit vector in the direction of that force here, so we can actually recover the formula for the gravitational force, and it's right here. This is it. That's it. The book has a slightly different formulation of this. Also, physics majors, you may have seen this written in a slightly different way, maybe with different letters to represent things. But this is the basic idea. This is essentially the length of the vector. This is a unit vector in the direction of the force, or I should say this is a unit vector in the direction of the force. But in essence, it's doing what you would expect. It's pulling everything in. And based on this figure, you can see that the force increases the closer you get to the object, and it decreases the farther away you get from the object. And that makes sense intuitively if you think about gravity and, things like stars or planets. Let's take a look at it in Mathematica. Let me switch here. That is this one. So here I used Mathematica to simplify things a little bit. I made a gravitational constant variable, a mass variable, another mass variable, and I defined the function g as that vector field that we just derived. So here is that. And then remember, a vector in Mathematica is a list of items like so, x, y, z. So what I'm doing here is I'm taking that length that we found, the length of f, and I'm multiplying it. This is scalar multiplication by the vector x, y, z. Just a reminder, norm gives you the length of a vector. So norm gives you the length of a vector, and we're taking the norm of this vector right here. The power of 3 actually comes from the formula. So if you look back at the formula on the slides, actually here, I'll just do this. Here we go. This is where you're getting the cube. So it's basically what I'm doing is I'm doing this right here, and then I'm multiplying it by the vector x. That's what you're seeing on Mathematica right here. Oops, right, right here. That's what that is. All right, now I've got my function plotted. Remember, you can download this from Canvas. You can mess around with the masses. You can mess around with the gravitational constants. Maybe if you're on a different planet, for example. And then I'm going to use vector plot 3D to plot this function. So I fed it the function. I gave it some bounds for the component function or the variables, and this is what it produces. All right. So just as we would expect, the gravity is pulling objects into the center of that mass. So everything's getting pulled toward the center, in this case, the origin. And as you get closer to that mass, the gravitational force is increasing. So remember, the color here is indicating the increase or decrease in force. And the closer you get to where our mass is located at the origin, the more yellow the arrows are getting because the force is getting strong. The force is getting quite strong. And the further away you get, the gravitational force is less strong. You're further away from that pull. And that's what this is depicting right here. So yeah, cool stuff, huh? I think it's pretty cool. So mess around with that on your own. You can download it on Canvas. And let's look at another example. Sorry, one of the, this is what's called a gravitational field. So I kind of said it, but that's what it is. So in this case, because this vector field is modeling gravity, we often call it a gravitational field. It's associating a gravitational force vector to every point x in space. Okay, now for the electrical engineers, here you go. So suppose there's an electric charge Q, and we're going to locate it at the origin. Then according to Coulomb's law, there's an electric force F exerted by this charge on another charge, little q, located at a point with position vector x, and it is given by this formula right here. So this is very, very similar to the formula we just saw. It's just in a different context now. It's very, very similar. You can almost think of it as like, uh, this was like G, and then you had M1, M2, and then you had a unit vector in the direction of the force dividing by this length right here, and so on. This is the distance between the two charges in this case. What is this little epsilon? Epsilon is what it's a constant related to the permittivity of free space, basically how much space, how dense the electric field is allowed to be based on the space that you're working in. Um, and you can look it up on your own, and you will learn it. You'll learn about it in engineering courses as well. So this is just a general formula. Sometimes physicists actually prefer to instead consider the force per unit charge. So what they do is they take this vector field and they divide it by q. Divide it by q so that you can look at the force per unit charge. These q's are going to cancel, and so then you're left with this. And this is what we call an electric field of the charge, capital Q. All right, so let's take a look at that one in Mathematica as well. That one I've got down here. And I actually plotted both, but same idea. There's this epsilon number, depending on the permittivity of space. Here's one of the charges, little q, charge big Q. I defined this function here, kind of using the same structure I did in the previous example. And then for the electrical field, I just divided this by little q. Yeah, so you see this one has little q, this one does not. And then I plotted both. In this case, I plotted them separately. So here you go. This is what that one looks like for those particular choices of charge. Particular choices of charge. And again, the color indicates the magnitude of the vector at a point. So this is the vector f. Now, E, or L as I called it, is when you look at the force per unit charge. This is just dividing by Q. So slightly different. It's really just kind of changing the magnitude in this case. Oops, there you go. And you can mess around with it. So enjoy, enjoy. All right, now let's talk about a very, very special kind of vector field called a gradient field. These ones are going to be very important for what we study for the rest of this chapter. So the vectors in the previous two examples, and frankly, just lots of the examples I've been talking about, are examples of force fields, literally force fields. So if you think about force fields in science fiction, this is what they're talking about. It's just a vector field that describes a force at every point in space. So those force fields that prevent the torpedoes from getting to the Enterprise, for example, they're essentially just like an electrical field that has a really, really, really strong force at some boundary edge, so that when something hits it, it can't permeate the force field at that point. But it's a force field, so it takes place over all of space in some sense, and you want to concentrate the field in different places, right? That's the basic idea. Um, so, okay, now recall if f is a scalar function of n variables, then the gradient is a vector of all the partial derivatives. So the gradient of f is a vector of all of the partial derivatives evaluated at all of the points, right? So in other words, for each point x in n-dimensional space, the gradient is assigning a vector called, del or gradient f to that point. And that vector is giving us the direction of steepest ascent. So in other words, the gradient is quite literally a vector field. The gradient vector is a vector field. Not surprisingly, it's called the gradient vector field. And it is literally doing this. It is providing you a vector field that says the direction of steepest ascent at every point. That's it. Okay. Um, just to look at some specific examples to take it down to 2 and 3 dimensions, if f is a scalar function of two variables, then the gradient vector field is just this. Oops, sorry, this right here. Partial x in the I direction, partial y in the y direction. You can write it using this notation. And if f is a scalar function of three variables, it's the same idea, except now you've got three partial derivatives. That's it. And this works for any number of partial derivatives. All right. Okay, so this one, let's see. So this one, I want you to try to compute this on your own. And then what we will do is we will look at both of these on Mathematica. So think about this one for just a moment. Find the gradient vector field of this function, and then we're going to plot it on Mathematica. Find the gradient first. So think about it for a moment. All right, now say something out loud about how you're gonna compute the gradient, and then hopefully you can compute it pretty quickly. All right, here we go. So the gradient is just the vector of partial derivatives. So when you compute the gradient, you're going to have these partial derivatives here. This is actually a figure from the book, but we're going to look at the corresponding figure in Mathematica here in just a moment. Yeah, so one thing to notice about this is the gradient vector field is all of the vectors that are orthogonal to the level curves, right? So this is the same thing that we saw before when we were talking about the gradient when we first introduced it back in chapter 14, right? So let's look at what this looks like in Mathematica. Okay, here we go. So for this one, what I did was I just went ahead and defined the vector function, x squared y minus y cubed. Then I wanted to show both of these graphics items on the same graph, and that's what you're seeing here with this picture. Oops, sorry. Let me click on this. Yeah, that's what you're seeing here. So remember the contour plot. The contour plot is giving you these level curves that you see in the background here and giving you this color gradient that you see over, the full fill-in colors. The vector field is these arrows that are overlaid. And so this is where things get really, really interesting. And it's really revealing how these vector fields are related to these scalar fields. So if what you remember, you want to think about what F really is here. F is describing a surface in space. So this is a two-dimensional, I'm sorry, this is a function of two variables. So its graph is going to be a surface in three space. So maybe even think about it in terms of gravity, right? Think about it in terms of gravity and like maybe a mountain range. That's what this is depicting. The vector field here, these arrows are kind of showing you how the rain, well, the opposite direction, but how the rain would flow down that mountain, except in the opposite direction. um, so remember, the gradient gives you the direction of steepest ascent. So when it comes to the analogy of rain flowing down a mountain, you need to take the opposite of the gradient, and that would be basically like going down instead. So this is what you can see here. Remember, the colors are denoting the magnitude. So you can see right here, you're actually going to have a saddle point, and that's why the vectors are smaller here. The direction is given by the direction of the arrow, but the magnitude is not very large when you're at these saddle points, because this is kind of like the, I mean, saddle points, right? I can't do it exactly, but the water is not flowing very quickly around these points. But then as you start to get to places where the mountain tips or like the surface starts to curve down a bit, you can see the water increases its speed, right? Of course, this picture is a little bit misleading because this is showing you how the water would actually speed up. So it's kind of reversed, but I think you get the idea. Again, you can play around with this. This command here is just having, so see here what I did was I used Mathematica to compute the gradient. I didn't hand compute it, which is not too hard, but here I had it compute the gradient. And then I'm evaluating that gradient at each one of these points. And then I'm plotting those results. The show command is just letting me show both of them on the same picture. If you didn't have the show command, what you get is you get two separate graphics items, just like we saw here. No show command, two different graphs. All right, so you can check this one out and mess around with it too. All right, okay. Now let's talk for a minute about conservative vector fields, and we're going to learn more about them throughout the chapter. So what's a conservative vector field? A vector field F is called a conservative vector field if it is the gradient of some scalar function. That's the basic idea. So a conservative vector field is called that because that means there exists a scalar function such that this vector field is the gradient of that scalar function. And in this situation, we call that scalar function f a potential function for the gradient f. Not all vector fields are conservative, so that's one thing to keep in mind. Not all of them are conservative, but many, many that arise in applications are conservative, and that's why they're so special. We're going to see why this terminology is used. We're going to see why we talk about, or why we're using the word conservative, and why we're using the word potential here. If you're a physics major or an engineering major, you may already know why. It's going to be, you can already see the punchline coming. It's just we have, geez, how many sections? 2, 3? We'll get the punchline in, I think, 2 sections, but I'm not sure. Anyway, that's what a conservative vector field is. So here's the big idea. When you hear somebody talk about a conservative vector field, then what they mean is that they can find a surface or a hypersurface described by a scalar function where if I were to compute the gradient of that function, I would get the vector field f. That's what it is. All right? Okay. Oh yeah, so some helpful Mathematica commands. This I already talked about, so there's not much more to talk. They were already kind of peppered in. Mathematica can help you with a lot of things. Remember that vectors are denoted by curly braces and your components are separated by commas. Vector plot gives you 2D vector fields. Vector plot 3D gives you 3D vector fields. And you can download that Mathematica notebook to mess around with it if you'd like. But on that note, let's play. So this lecture is not too long. That's always kind of nice. Main takeaway, just make sure you understand what a vector field is. Make sure you understand what a gradient vector field is. Make sure you understand the definition of a conservative vector field. And we're going to expound on those ideas more in the next sections, all right? But I'll stop here. Thank you all again for listening, and I'll see you next time.